Hello, welcome to Basics of Noise and its Measurements. Today we are going to change gears and we will discuss some details about instrumentation, because whenever we take measurements we use a lot of instruments and equipment to take these measurements, and it's important to know some basics which will help us pick the right type of instruments when we are in this business of making noise related measurements. So that's what we are going to discuss today, considerations while deciding instrumentation. So what I'll do is I'll first draw a schematic layout of one noise related setup. So suppose I have some noise source and I want to measure it using a microphone. So that's my microphone. There is maybe a preamplifier attached to it. So we have learnt significant details about microphone. So this microphone may be connected to a power supply. And this power supply is such, so this cable, it's not one single conductor, but there may be several conductors. Some conductors may be drawing power to this microphone, and some conductors may be sending signal back to this power supply unit, and maybe from here I have another port in this power supply box, and from here I get my noise signal out. So I will not call it noise signal, I will call it measured signal, because noise is always sometimes also used as something which is unwanted. So I get measured signal which comes out of this power supply, and then so this is analog. It is analog data, and then I convert it into digital data. So using this something called A to D converter. Analog to digital converter, or some people call it ADC, analog to digital converter. So here inside whatever signal is going in, it's some current or some voltage. What I am getting out is a string of zeros and ones. It's not a current or a voltage, it's a string of 0 and 1s. So this is digital data, okay, and this I feed it to a computer which is having some hardware to actually store data, convert that data, interpret that data. So this is data acquisition system. So this will be having some software and also hardware. So this is the overall schematic, one schematic, and this data runs on power, electric supply. This could be 220 volt AC, or it may also run on DC source, for instance a laptop, so it may run on a DC power supply also. This will also require some powers, typically these guys run on some DC sources, and this will also require some power supply. Now you can have adapters, typically these require DC power supply, but a lot of times we have some adapters which convert this 220 volt into DC and then feed it to the system. So this is the overall thing, and what we are going to discuss today is about this A to D converter and its importance. we will discuss about other things maybe at a later point of time, but I think it is important to understand about A to D converter. So, A to D converter, it converts analog signal to digital signal. Okay. So, what is an analog signal? So, suppose you have a sine wave, this is time, let us say this is voltage. This is an analog signal because you have infinite number of points between in a time interval. Okay. And what this A to D converter does is, first thing is it breaks it up into discrete points. That is the first thing it does. So, it does not, it looks at this, it actually does sampling of it. Okay. So, each of these, let us say this is Vk. So, it actually converts this analog signal into Vk, that is the first thing it does, and then it represents this Vk in a string of 0 and 1. So, first it will measure Vk at different points, and then corresponding to each value of Vk it will send out a string of 0 and 1s. That is what it does. Okay. Now, these A to D converters are, they have several specification parameters, but one very important parameter is called number of bits. So, you may have an A to D converter which may be a 12-bit device, you may have a 8-bit device, you may have a 16-bit device, you may have a 24-bit device, it could be anything. I mean, typically it is some even number. So, what does an 8-bit device mean? What it means is that suppose the AD converter can sense voltages over a range, suppose sense 0 to 1 volt. So, it has a range of 1 volt. Okay. It has a range of 1 volt. Now, let us say that the A to D converter, 1-bit device, we will start with 1-bit device, which means it will send out two possible signals. It will send out a 0 and it will send out a 1. These are the only two possible numbers it can send out. Okay. So, what does that mean? It will say, okay, if I send out 0, then the data acquisition system, you interpret it as 0 volts. If I send it out as 1, then you interpret it as 1 volt. Okay. These are the two possibilities. So, in this case, I cannot sense half volt accurately. I cannot sense half volt accurately, right. So, in this case, the resolution is what? 1 minus 0 is 1 volt. If it is a 2-bit device, then what are the parameters it will send? 0 0, 0 1, 1 0 and 1 1, right. So, then this will correspond to 0 volt, this will correspond to 1 volt and these will correspond to something intermediate, right. So, I can make this 0.33, 0.66 and so on and so forth. So, maybe the protocol could be, if I send out a string of 2 zeros, consider it as 0, 0 1 0.33, 0 0 0.66, 1 1 1, right. So, I can extend. So, what we see is that here resolution is 0.33 volts, and we can actually have a formula. So, resolution is equal to what? Range over 2 to the power of bits minus 1. Okay. So, if it is a 8-bit device, resolution is range divided by 2 to the power of number of bits, which is 8 minus 1. Okay. Now, I have a to D converter here. This is a 24-bit device, 24-bit device. So, for a 24-bit device, and its range, it says, is plus minus 34 volt. Range, it says, is plus minus 30 volts. So, that means its range is 60 volts. So, resolution is equal to 60 divided by 2 to the power of 24 minus 1. Okay. And because this 2 to the power of 24 especially is extremely large, I can approximate it as 60 divided by 2 to the power of 24. If this number of bits was very small, then 1 mattered, but now it does not matter. And this is, so what is this thing? This is 2 to the power of 24. So, we know that 2 to the power of 10 is 1048. It is approximately equal to 10 to the power of 3. So, 2 to the power of 20 will be approximately equal to 10 to the power of 6, and 2 to the power of 24 will be approximately equal to 10 to the power of 6 into 2 to the power of 4. So, 2, 4, 8, 16. So, it is 1.6 into 10 to the power of 7, right. So, here the resolution will be 60 volts divided by 1.6 into 10 to the power of 7, that is 6 over 1.6 into 10 to the power of minus 6 volts. So, now you would be wondering, why is this important? But first we have to learn that how to calculate the resolution of this A to D converter. This is important, because if we are interested in making very small measurements, then the resolution of the A to D converter has to support that kind of a measurement. And we have seen that a lot of times sound pressure levels are extremely small, and then a lot of these microphones, their sensitivity is not 0 dB or 1 dB or 10 dB, it is negative 20 dB, negative 30 dB. So, these small voltages, small pressure fluctuations are converted into even smaller voltage levels. Okay. So, we have to have some idea before we start taking measurement, that what kind of voltage measurements we will expect from our measurement experiments. And once we have that idea, then we have to make the right type of selection for this A to D converter. So, I will give you an example. So, suppose I think I have a 60 decibel sound. Okay. In that case, PRMS equals 10 to the power of 60 divided by 20 into 2 into 10 to the power of minus 5, and if you do the math, you get something like 2 into 10 to the power of minus 3 pascals. Actually, excuse me, it's 2 to the power 10 to the power of minus 2. And let's say a microphone is, and let's say I am measuring this sound using a microphone which has a sensitivity of minus 40 decibels, and reference is 1 volt per Pascal. You've seen what is that, right? So then what does it mean? That it will give me, so this means minus 40 dB equals 20 log y divided by y ref, and from this I calculate y equals 10 to the power of minus 40 divided by 20 times 1, and that gives me 0.01 volts per Pascal. It will give me 0.01 volts per Pascal. So each Pascal I generate, it will just give me 0.01 volts. Now I have to sense how much? Maximum pressure I will sense is 0.02 Pascals. So maximum voltage generated will be 2 into 10 to the power of minus 2 into 1.414. Suppose it's a sine wave, then I have to multiply that by RMS. So this is the pressure times this number 0.01. So this comes to 2.83 into 10 to the power of minus 4 volts, right? So I should be able to sense at least 2.83 into 10 to the power of minus 4. No, I should be able to generate the this much, at least this much. But when I make a measurement, I will not just measure the maximum pressure. I will like to measure some intermediate values also, maybe at least 10 values. Suppose it is a sine wave, I like to get a good shape. So maybe resolution expected is equal to 2.83 into 10 to the power of minus 4 volts divided by 10 is, so I am going to round it off. So it will be 3 into 10 to the power of minus 5 volts, that is 30 microvolts. Okay. Now let us say that we have two A to D converters. First ADC A to D converter 1, its range is plus minus 5 volts and it's a 16-bit device. Then what will its resolution be? Resolution equals range, which is 10 volts, divided by 2 to the power of 16, right? It is 2 to the power of 16 minus 1, but I am just ignoring minus 1. So this is equal to 10 divided by 2 to the power of 16 is roughly 65,000. I am just approximating it, okay? And if you do the math, you get roughly something like 6.1 into 10 to the power of minus 4 volts, okay? So if you use this instrument, you will not even be able to sense this number, the maximum voltage. So you use this instrument and you do all the recordings, you have a great microphone, everything is working fine, but on the computer you will see nothing. So you will say, what is happening? Maybe something is bad or something. No, you selected a wrong A to D converter. So then you say, okay, what should I do? So you go and spend more money and you go and buy a more expensive A to D converter. And let's say this one has a range of, so ADC2, it has a range of plus minus 5 volts, but it's a, let's say, 24-bit device. Okay. So, then what is its resolution? Resolution is 10 to the power of 10 volts divided by 2 to the power of 24, and that minus 1, it is approximately equal to, if you do the computation, 2.4 into 10 to the power of minus 6 volts. Okay. So, you see this and you compare it, how much do I want at least? I want at least 30 microvolts. So, this gives 10 times less than this. So, this is going to meet my need. So, this is a very important consideration, A to D converters, and what I have explained to you is how to go around making the right type of selection, at least in context of A to D converters, from the standpoint of only one parameter, which is how many bits it has. There are several other parameters associated with these converters. So, we will look at some of these parameters also in the next class, but today we just wanted to terminate our discussion at this point of time, and then we will also look at other parameters which are important as and when we develop complex noise and sound measurement related setups. So, thank you very much, and we will see you next day. Bye.